Hello, everyone, and thank you for joining us today. Welcome to day two of Megger's virtual Substation Best Practices seminar. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of each presentation. Today, we will have two separate presentations with their own Q&A sessions, so please stick around after so we can get to our next presentation as quickly as possible. The presenter for our first segment today is Ken Petroff, Transformer Product Manager. Also, to assist with the question and answer session, we will have two panelists joining us. Dinesh Chajir, Technical Support Group Manager, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Ken.
Thank you very much, Michael, and thank you all for attending this best practices seminar today. Today we will be focusing on best practices for transformer winding assessment with a focus on turns ratio, winding resistance, and excitation current. When we talk about transformer testing overall, we try to separate the tests into two major groups, the first being mechanical and the other side being insulation. Mechanical testing is what we're going to focus on today, so turns ratio, winding resistance, core excitation. There are other mechanical tests such as core ground or leakage reactance, but that will be covered at a different time, not today. Over on the insulation side, insulation resistance, this has been around for over 100 years. Line frequency power factor, dielectric frequency response, which is power factor over a wide range of frequencies, and then finally narrowband DFR. Of course, there's other tests that we didn't mention here, but when you do think about transformer testing, try to think about the tests in these two separate but important functions, mechanical and insulation. I do want to mention that next month there will be another best practice seminar where we are going to focus on insulation, so make sure to check your inbox for that link. But as I mentioned earlier, we are going to focus on these three mechanical tests today, and the first of which will be a turns ratio. But in general, what issues can be found with these mechanical tests? We are looking for problems with the windings, shorted turns, broken strands, any kind of winding deformation. We are also looking for problems with the core, such as shorted laminations or ground faults. And then finally, with mechanical tests, we can look at the tap changer. With turns ratio testing, you can look for continuity, and with winding resistance, you can look for high contact resistance. That is what Samir will be covering when he talks about core excitation and winding resistance. But for the first part of this best practices seminar, I will be talking about transformer turns ratio testing. This will cover the basic concepts of turns ratio testing, when and why the turns ratio testing is performed, what are some factors that may impact your results, and then finally we will take a look at the latest turns ratiometer from Megger, the Ttru3, the instrument itself, and then some of the software that is used. So getting started, looking at some basic concepts, and why do we concern ourselves with turns ratio? Well, if you look at the power grid, all the way from extra high voltage to the high voltage lines, then down to the distribution grid, there are transformers all throughout the system. Your power plants, your factories, and then once you get the distribution grid, of course, you have transformers that take these to your city networks or that are coming from your solar farms and wind farms. So it's important to consider turns ratio testing based on the sheer number of transformers there are in the electrical system. Turns ratio testing is one of the simplest tests that you can perform to get a baseline level of functionality to confirm that your transformer is working. Now, given that we have so many different transformers throughout the grid, they come in all different shapes and sizes, from your pole mount all the way up to your transmission class transformers. And it's important to note for you sly people out there that these transformers are not to scale. This is just an example of some of those that you may see out in the field. So what is turns ratio? In a transformer, in its simplest terms, it is the number of primary winding turns divided by the number of secondary winding turns. And this gives you your turns ratio. So that's all good. In the factory, they know how many turns they put on the primary, they know how many turns they put on the secondary, they can get a very exact turns ratio. But in the field, you're not going to know how many exact turns are on the primary and secondary. So what are you going to do? You're going to apply AC voltage to the winding that is greater than or equal to the line frequency of that transformer. You will measure that voltage that you are exciting with, and then you will measure the voltage on the corresponding winding on the other side of the transformer, and then divide those as was shown in that previous example. There are some assumptions that we make when we talk about the transformer, and what you're looking at on the screen now is the transformer equivalent circuit. And that part highlighted in green is the turns ratio that we are considering. The assumptions that we're making is that the no load voltage ratio is equal to the turns ratio. And when we say no load, we mean open circuit or negligible impedance influence. So the excitation impedance is much greater than the short circuit impedance. When we talk about turns ratio, we have a couple terms that we can refer to. The first being TNR. This is called transformer nameplate ratio. This is mostly going to be phase to phase when you are comparing your turns ratio results. But then we also have TTR, which is measurements from phase to neutral. You may have also seen this reported as TVR, but for all intents and purposes, TTR and TVR are equivalent. So we will only be referring to turns ratio in terms of TNR and TTR moving forward. Now, so far, I have only been showing single-phase transformers. Single-phase transformers, the TNR and the TTR are equivalent because there's no phase-to-phase or phase-to-neutral. It is a very simple single-phase transformer. However, once we start getting into three-phase transformers, you can have configurations such as a YN, YN0. In here, you will have TNR and TTR values, and it just so happens that those are going to be the same because there is a neutral on both the primary and the secondary winding. Likewise, for DD0, this does not have a neutral, so on either side, so the TNR and the TTR values are going to be the same. However, once you get to transformer configurations such as DYN1, one side will not have a neutral and the other side will. So the TNR and the TTR values will not be equivalent. Sometimes during your testing, this can get you caught up if you're getting a value that's, let's say, the square root of 3 different than what you expect. So it's important to keep in mind whether you're looking at your turns ratio with respect to TNR or TTR, phase to phase or phase to neutral. Of course, there's many different standards out there that describe how to evaluate the turns ratio. So you got your IEEE, your NETA, your IEC. In general, you are looking for the turns ratio of plus or minus 0.5% for your transformer in order for it to have an acceptable reading. So this leads us to how is it evaluated. So you're going to compare your measured value to your nameplate calculation. And again, look for that plus or minus 0.5%. One thing that I want to note here is that the nameplate calculation is not the actual ratio of the transformer itself. In one of the first few slides, I told you that the turns ratio was the number of primary turns over the number of secondary turns. That is the actual turns ratio of the transformer, but that is not what is put on the nameplate. What is put on the nameplate is the voltage that the transformer is going to operate at. And those voltage steps do not equal the turn steps within the transformer. And that is why that plus or minus 0.5% error is allowed. That's the reason for that error margin. And just to show you why that is important, I have an example here of some turns ratio testing that was done on a transformer. One where we were comparing the nameplate error. So this is across 7 different taps. And if you look, you can see that the turns ratio, is within acceptable limits from 0% to minus 0.2%. But you'll see that after every few taps, it appears that there's a drastic swing in the percent error. But again, we're looking at the nameplate percent error. If we look at the actual number of turns, we can see that the change in percent error is actually much, much smaller than what it would be when looking at the nameplate. So just because you see this kind of change in percent error over taps does not indicate a problem with the transformer. It's just that the nameplate percent error is going to deviate more than the actual turns error. And you're not going to have access to this actual turns error. The only people who will have access to this are the transformer manufacturers. So I just wanted to bring that up before we get into the why and the when of transformer turns ratio testing. So when is turns ratio performed? It's performed during design and manufacturing. Typically, the transformer windings will be tested on a test core before they are put in on a production core, and all of that testing will be done before the core is submerged in oil. If it's a liquid type transformer, which is mostly what we are talking about here today. So it's tested a few times throughout the manufacturing process. Testing is done during acceptance and commissioning. You want to make sure that no damage was caused during the transportation of the transformer, so you're going to do a thorough check on that before the first energization, if you will. Maintenance during your scheduled testing. Turns ratio, again, is one of the easiest and fastest tests that you can perform to ensure a base level of functionality for your transformer. And then finally, if you have unexpected events such as faults or damage, again, you'll want to use turns ratio to see if the transformer is even viable at that point. So why do we do this testing? Again, during design, we want to validate that the windings are wound correctly. We want to validate that the core is transferring that magnetic flux properly. And of course, turns ratio testing isn't going to be the only testing that is done during design. They're going to do winding resistance, they're going to do core excitation, but Samir will get to that in the second part of the best practices today. Of course, we're looking at quality. When you're talking about single phase or 3-phase transformers, you want to make sure that you have the correct phase displacement. In addition to the turns ratio, you got to make sure that the polarity is correct, that the winding wasn't put on in the opposite direction. Verify that all of your connections are made properly, and verify that your tap changer is going through all of its positions and providing for the flow of electricity. When you're doing your routine maintenance, of course, you want to verify to your previous measurements, make sure that nothing has changed over time. And then if damage is suspected, you can look for shorted turns, open windings, or again, tap changer malfunction if you see no continuity during your turns ratio testing. So that is the when and the why. So what are some factors that could impact your results? When we think about TTR, there's a few different areas that could impact the results. The first being test voltage. If you have 1 millivolt that you're injecting into a transformer, it is not going to generate sufficient flux to transform that voltage properly. So you need more test voltage in order to get an accurate turns ratio measurement. This relates to whether you're exciting the transformer in step up or step down. So whether you're exciting the secondary winding or you're exciting the primary winding, that will influence the amount of test voltage that you can generate. Whether you are injecting single phase or 3-phase, this can also influence your measurement. And then finally, the transformer configuration that you are testing. Again, not only that TNR-TTR relationship, but another impact as well. So when we look at test voltage, this is what I was alluding to earlier. When you don't inject enough voltage, you will not get a proper turns ratio measurement. So in this example here, a few different voltages were injected on the primary winding, starting with 8 volts and then moving on up to 125 volts. And you can see that at 8 volts, the turns ratio measurement would be considered a fail according to the standards. But by simply increasing the test voltage up to 125 volts, you see that you have a acceptable percent error here. And what you'll notice is that the percent error increase the percent error improvement, I should say, tends to trail off after a certain test voltage. And in the testing that we've seen, above 125 volts or right about there is the max improvement that you're going to see. So you want to get up to and around 125 volts. Another example here, looking at some multiple phases. Again, this transformer was tested at 3 different test voltages, 8, 24, and 48. On phase A, we see an improvement in turns ratio of about half. On phase B, we see the same relative improvement of about 0.15%. And then C, we see a little bit more drastic improvement. But again, the point is that as you increase test voltage, you will get a more accurate percent error for your transformer, not on just single phase, but also on 3-phase. This is an example of different test voltages. On this particular transformer, it was tested with 100 volts step down applied on the primary winding. And what happened during commissioning was that the tap 1 failed the ratio. You can see it's at 0.51% highlighted in red. By inducing 250 volts on the primary through the step-up method, the tap 1 passed the ratio, and on average, you see a 0.21% improvement in turns ratio. So not only on that failed tap, but on all of the taps, there was an improvement. This brings me into my next discussion because if you will note in the top right-hand corner here, there's 250 volts step-up measurement voltage, but 20 volts was applied on the tertiary, and this is what we refer to as the step-up method of testing. So step-down ratio testing is when you inject voltage on the high voltage winding and you induce voltage on the low voltage winding. So for example, if this was a 10-to-1 transformer and you injected 100 volts on the high voltage winding, you would get 10 volts on the low voltage winding. On the other side, when you inject voltage on the low voltage winding, this is called step-up ratio testing because you're going to inject that 10 volts on the low voltage, and by a factor of 10, you will then get 100 volts on the high voltage winding. So step down versus step up is how you are applying or exciting the transformer in order to get your test voltage. An example of how this can be used, here we see a transformer turns ratio percent error improvement when we look at single phase excitation step down versus single phase excitation step up. And what's important to note here is that the test voltage, the excitation voltage for the step down was 80 volts, while in step up, only 8 volts was excited with, but you can see the great improvement to the turns ratio percent error. Again, this is because on this transformer, we were creating more test voltage on the primary as opposed to just injecting 80 volts on that primary. Some more examples here of 3-phase step-down excitation. So this is exciting all 3 phases at the same time. By injecting 48 volts, we were getting a percent error that went into the error range above 0.5%. But by flipping that around and injecting the voltage on the secondary, we were able to improve the percent error quite drastically by inducing up to 250 volts rather than injecting 48 volts on the primary winding. So you can see as I toggle back and forth between these two that step down versus step up. Step up will get you a much higher test voltage on the primary than you will get with your step down excitation. Another factor that will impact your results is whether you're exciting a transformer phase by phase or three-phase. So in the example that I'm showing here, when we do single phase excitation, what I mean is that you are exciting one phase at a time and then switching to the next phase, as you can see demonstrated by this vector here with the different phases that are being excited. Three-phase excitation means we are exciting all three phases at the same time. And what you will see here is that the percent error, simply by exciting all three phases at the same time, improved over all of the different taps. Lastly, your transformer configuration will impact your turns ratio result, especially if you have a delta secondary winding and you are injecting single phase on the primary winding. When you have a delta winding, any of the unexcited phases will load down the transformer and it will impact your results. So this is not only applicable to three-phase two-winding transformers, but three-winding transformers, auto transformers with tertiary are also will also exhibit higher percent error if you're only exciting one phase on that primary winding, leaving the other two phases unexcited, which will load down the transformer. So how does the TTRU3 help you with all of these different factors impacting your results? The TTRU3 has a true three-phase output. So as we were just talking about with single phase versus three-phase, you do get improved accuracy versus that single phase switch testing. It also allows the testing to be done very fast, 10 seconds for all three phases, and it enables you to test phase shifting transformers, something that is not easily done with single phase switched output. The TTRU3 guarantees accuracy of plus or minus 0.05%. We do this across the full operating range of the instrument from minus 20 to positive 50 C. We do this by inducing up to 250 volts using a patent-pending three-phase step-up method. So we use less excitation voltage to excite the secondary winding and induce up to 250 volts on that primary to get you that test voltage that you need for accurate measurements. And then finally, we have a touchscreen interface that comes standard on all of the models, and we provide you with concise reports. That touchscreen interface gives you on-screen vectors. We provide you with percent error graphs, and when you export, you get reports in Excel and PDF. So it makes reporting to your supervisors, your managers, very easy when you're using the TTRU3. Some of the tests that are conducted with the TTRU3, while it is a three-phase, true three-phase device, we can test single-phase switched if needed. If you want to try and match results to your historical results, that is why we have it. And then also, not every transformer is going to operate 100% correct all the time. If you have a damaged winding, then you need to be able to excite one phase at a time to determine if the other two windings are still functioning or to try and isolate that problem winding. While we do like to talk about the step-up capabilities of the TTRU3, it should be noted that we can also perform testing step-down. This is important if you're doing any testing on, let's say, CTs or PTVTs. You will need to do step-down testing. You will need to inject small amounts of voltage in order to avoid saturating like a CT core and to get up to those high ratios that you see on those CTs and PTVTs. We will provide you with excitation current measurements. Samir will be talking about this more after I'm done. But with the Ttru3, we will give you that excitation current measurement in both the step down and the step up measurement. When we do step up, we tend to use a lot more current since we are exciting that secondary winding. So it does provide you with a bit more resolution than you would if you were doing it simply step down. Vector recognition and validation. So we do have functionality within the Ttru3 where you can say, I have a primary and secondary winding, tell me what phase shift it is. And it will come back and it will tell you if it's a DD0 or a DD6. In addition to that is vector validation. So at the beginning of each test, we do a 1-volt probe test where we validate that the leads are connected properly, that there's no short-circuited windings, and during that time we will verify that, yes, you said it was a DYN1 and you have connected it as a DYN1. If you selected the wrong vector, say a DYN7, the Ttru3 would alert you and tell you that to check your leads or check your vector selection to make sure that you're running the test properly. You need to make sure that you have the correct vector transformer configuration when you're doing your testing, because if you were to put a transformer with an incorrect vector into service on a system that was expecting a different configuration, you could have catastrophic failures. Building on that vector validation, we do phase deviation measurements. So let's say, yes, it was a DYN1, but how far off each phase is it deviating? You see this will happen sometimes when you have shorted windings and turns, you'll see a higher phase deviation. So it's important to also show that measurement alongside your excitation current and your ratio. As mentioned earlier, we do phase shifting as well. So if you have a regulator or something with a abnormal, I would say, phase displacement, let's say 7.5 degrees or minus 7.5 degrees, the Ttru3 being a true 3-phase ratiometer allows you to test those type of transformers very quickly and easily. There's also a test that's not well known in the United States, but it's referred to as magnetic balance. This is a ratio test, but rather than measuring the turns ratio across the primary to secondary, it is a turns ratio measurement that looks at the primary windings to other primary phases. So if you excite phase A, it will look at the ratio of induced voltage on phase B and phase C. It's typically used in India during transformer construction to look for any problems during transformer, when they're winding the core or winding the winding, or when they're putting the winding on the core. But it can also be used to validate the state of magnetization within the transformer, which is where we would expect most people to find value in that software feature. So the true 3-phase, when you go to set it up, you have some high voltage leads that you connect to the primary, and you have some low voltage leads that you connect to the secondary. And as was discussed earlier, you can do single phase switch testing, which goes from phase to phase to phase, or you can do 3-phase testing, which excites all 3 phases at the same time. I mentioned earlier that simultaneous 3-phase testing is about 10 seconds, which on average is about 66% faster than switch 3-phase if you look at all the different turns ratiometers that are out there. If you're doing a single test on a transformer, that's not really going to get you all that excited. If you are doing any kind of testing on OLTCs, you start to see vast improvements in test time. So 10 minutes if you're only running through one tap, but then you can save up to an hour if you're doing a full-blown commission testing where you're going through all the DETC and OLTC taps. And as mentioned, the Ttru3, you can do step down where you excite the primary winding, or you can do step up where you excite that secondary winding. And here I am showing the red highlight moving from the primary winding to the secondary winding to show where that voltage is being, where we're exciting the transformer. Now, what do we do to help you ensure that you have connected your leads properly to the transformer? Part of The importance of this testing is making sure you have the correct vector selected and that you are connected to the transformer properly. Well, we have leads that are easy to identify from the ground. We have a red jacket on our high voltage winding leads, and we have a black jacket on our low voltage winding leads. So you can very easily tell if the correct leads are going to the correct side of the transformer. In addition, we have color-coded clamps for each of the phases, so A, B, C, and neutral. And again, this just makes it very easy to tell that you have the leads connected in the proper order. When you go to do your testing, if it says, hey, you selected the wrong vector, check your vector selection, check your leads. This makes it very easy. You don't have to get back up on the ladder, back in the bucket truck. You can quickly tell if you have it connected properly or not. Which brings us to the software. So not only do we have hardware that makes it easy for you to see if you are connected to the transformer properly, we also have software which uses less words and more symbols, which means that it is a lot easier to get trained on this device. And we have made the software that runs on the PC and the 7-inch display identical. So you don't have to spend a lot of time learning how to use two different interfaces. You can learn it on the PC and then start using the 7-inch display right away. And we facilitate that learning process through simulation mode. So you don't need a physical device to do any training with the Ttru3. You just need to download and install the software. When you first launch the software, it will look for a Ttru3. It will ask you to make sure that it is connected to the PC. After a few seconds, it will time out and say that it cannot connect to the Ttru3. Do you want to enable simulation mode? You will say yes, and at that point, it will bring you to the home screen, which will enable all of the different software features that are available on the instrument for you to learn and get trained on. When you do go and run that first quick test, because that is where the majority of people will go to, I encourage you with the software to first go to the quick test so you can see just how easy it is to set up and run a turns ratio test. You will first want to match your nameplate to the vectors that are displayed on screen. So here we have all of the labels for the different vectors, so H1, H1, H2, H3. Not every turns ratiometer shows the vectors on screen. Sometimes they require you to enter in, let's say DYN11, but if you're entering in the letters and numbers DYN11 and that's not available on the physical nameplate, then you're left guessing. The Ttru3 takes away any of the guesswork that you may be incorporating by just showing those vectors directly on screen. And then finally here, when you do set up your test plan, what we provide you on screen is percent error graphs when you are going through your testing. So whether you're testing a 5-tap pad mount transformer or a 33-tap OLTC, while yes, it is good to look at each individual phase, the excitation current, the turns ratio, the percent error, sometimes you just need a concise way to make sure that all of your taps are within the percent error limit. And we provide that for you on this easy to read graph. Finally, when it is time to export and report your results, we provide that same information that you were seeing on this previous screen right in an Excel report. Depending on the information that you filled out in the test plan, the asset details, the test conditions, the nameplate, all of that will be present in the report itself, along with all of your turns ratio results, the percent error, the excitation current, and the phase deviation. So again, making it very easy for you to not only run and execute your tests, but for you to report the results, whether it's to your supervisor, to your manager, or to the company who has contracted you to do that testing. So in summary, talking about the best practices for the transformer turns ratio testing, there are a number of factors that will affect your results. The first and most important is going to be your test voltage. There's a reason why there are different transformer ratiometers on the market, from your handheld TTR to your hand crank to the Ttru3. They all are able to source different levels of test voltage, and they all meet their application need. But in general, the larger the transformer you have, the more test voltage you are going to need, because that 1 millivolt is not going to generate sufficient flux and transform across the core to get to that other winding. Now, whether you're doing that turns ratio testing step up or step down, again, with step up, you need less excitation voltage to achieve a higher test voltage on that primary winding. While with step down, you're going to need more voltage, which will result in a heavier piece of equipment to do the same type of testing that you can do with step up. Single phase versus three phase. This is especially important if you are doing any testing with a delta secondary, whether that's on a 2-winding transformer or a 3-winding transformer. If you are doing single phase testing, the unexcited phases of that delta winding will influence your measurement. They will load down the transformer. So if you have a measurement that's on the hairy edge, you may want to bring in a 3-phase transformer to improve that percent error and give that transformer a passing grade. And of course, that brings it into the transformer configurations. Again, you could have a DYN1, a DYN7. You want to make sure that you have your leads connected to that transformer properly. You have to make sure you select the correct transformer when you're doing your testing, because again, you do not want to put the wrong transformer into service in a system that is unexpected. And then how does the Ttru3 help you with all of this? We give you that guaranteed accuracy with repeatable results from -20 to 50 degrees C. That guaranteed accuracy of plus or minus 0.05%. Again, when you have a transformer or turns ratio measurement that's on the edge, you want to have a turns ratiometer with the best accuracy, so that way you can say, yeah, even if I'm at 0.4%, my turns ratiometer is plus or minus 0.05, I know that my measurements are good to go. And the main way that we do that is through our patent pending 3-phase step-up technique. We use the transformer itself to overcome the voltage dependence that we always talk about with the test voltage. So with a smaller excitation voltage, we are able to achieve a higher test voltage on the primary winding, which gives us that accuracy that we guarantee. And of course, we do all of this by inducing up to 250 volts safely. The Ttru3 is the fastest true 3-phase ratiometer, clocking in at 10 seconds for all phases. And we do provide you with a truly simple interface. Whether it's the physical leads themselves that you're running up, 60 or 100 feet in the air, you can see the red jacket, you can see the black jacket, you can see the color-coded clamps to verify that you have made your connections properly. Then on screen, we're giving you those vectors. So again, as we were talking about over here, your factors impacting your results, your transformer configurations, we give you hardware and software to be able to verify that you have the correct transformer configuration for your testing. And then finally, we're going to give you graphs. We're going to give you Excel and PDF exports that are concise, that make it very clear to understand what's happening with your transformer, and make the company that you're doing your testing for, or your supervisor or manager, make it easy for them to understand exactly what's going on with that transformer. And with that, I have my contact information here, and I believe Michael's gonna hop back on.
Yep. Thanks a lot, Ken. So at this time, obviously, the presentation portion of the first segment has concluded. We'll take a few minutes to answer as many of your questions as possible. If you have any questions, you may submit them now into the Q&A box on the right side of your screen. As a reminder, we do have one more segment after this, so please stay tuned. So let's jump into the questions, and I'm going to direct the first one to Dinesh. Dinesh, can all types of transformers be tested with all the different tests?
Good afternoon, everyone. So this question is an interesting one. Reason being that you have various different kinds of transformers out there, dry type transformers, oil filled transformers, and then there are transformers like zigzag, non-NC configuration transformers. So certainly not all the transformers can be tested for all different tests. For instance, on dry type transformers, sometimes it is not recommended to do power factor testing because the numbers can be unusually high. The test that is recommended for dry type transformer more so is kind of tip up test. On the other side, for oil filled transformer, you may not want to do a PI test, which is an insulation resistance test with the ratio of 10 minutes over 1 minute reading. So based upon what kind of transformer you have, there are various standards out there, IEEE, IEC, and NETA ATS and MTS standards are out there that list what all field tests you can perform based upon the type of transformer you have, dry type or oil filled. Additionally, when you talk about now, if we talk about turns ratio testing, if you run into a zigzag or non-NC vector configuration diagrams, the method by which you would test would be quite different than testing a regular DY or like YY transformer. So based upon the configuration of transformer and the type of transformer, your testing practices and what kind of test you do would vary.
All right, thank you, Dinesh. The next question is going to be for Daniel. Can a magnetized core affect turns ratio results?
Thank you, Michael, and hello to all the attendees. Thank you for joining us to this session. So certainly, yes, and Samir will touch on this briefly on his presentation when he talks about what kind of issues you can detect when doing excitation current. So yes, remember that the core, right, is one of the most important components that you're testing with the TTR is highly involved, right? The core is there to provide that magnetic link between the windings. So yes, if the core is magnetized, it can certainly yield or affect the TTR measurements. The good thing is also remember that Ken also explain when you run TTR with a unit like with the TTR-U3, you also get excitation current values for that voltage. So it is also useful that you compare those to previous results. And remember, excitation current results will be voltage dependent. So if you are actually comparing those as well, make sure that the test voltage was the same between the two results you are comparing.
All right, thank you, Daniel. Dinesh, how can you have a TNR on a delta-delta? I don't think we can hear you right now, Dinesh. We might have lost your audio.
I apologize. I was on mute and I started talking. Sorry about that. This is an interesting question. Transformer nameplate ratio, that's what TNR stands for, transformer nameplate ratio. There are various different ways how you can represent a ratio of your winding turns or nameplate ratio turns. So TNR, as I said, like it stands for transformer nameplate ratio. And for a delta-delta configuration, as most of you guys may know that for a delta winding configuration, the line-to-line voltage would be the same as the phase value voltages. So a transformer nameplate ratio for a delta-delta would be the ratio of the primary line-to-line voltage to the secondary line-to-line voltage, which would be the same as the ratio of the phase values. So for a delta-delta configuration, TNR and TTR would be the same one, exact same thing. So that's how you kind of determine the transformer nameplate ratio for a delta-delta configuration.
Thank you, Dinesh. Our next question is for Daniel. What voltage injection is recommended for testing TTR?
Okay, interesting questions. And since in the sense that there is no rule written right on standards or recommendation based on valuing the nameplate or the transformer you're testing, just want to make sure that you're applying a high enough voltage to be able to induce voltage on the other side of the transformer. And also remember the aspects that Ken touched on his presentation in regards to doing step up versus step down. That will be more important. And again, no written rules. Look, if you can induce voltage on the other side, and also again touching or going back to Ken's points during the presentation, doing single phase versus three-phase excitation, it's also important, as three-phase excitation on a three-phase transformer will be a more accurate measurement.
All right, thank you, Daniel. Dinesh, this next question is, in auto mod, will the MWA optimize the proper applied voltage?
Again, these are very good questions, and these are some practical questions that you run into when you're out in the field. And before I answer that, just a I guess a simple note to all of the attendees that as important as the presentation is, these questions are equally important, and we're going to go through some of these questions, and after that Samir will talk about the winding resistance and the excitation current. So these are very interesting questions that are coming up. So coming to this question of using the auto test voltage mode when you're using the turns ratio test set, with the Megger winding analyzer unit, it has 3 voltage levels, 8 volt, 40 volt, and 80 volt. You can either select any one of those voltages, or you can select the auto mode. And when you select the auto mode, the test set would optimize the right voltage that should be used for a certain transformer. And I will give you an example that if you're testing a small dry type transformer, sometimes if you apply too much of voltage, you may also lead to higher excitation current, and that can give you a error message, excitation current too high, or in some cases the losses taking place because of excitation current may impact the accuracy of the reading. So if you leave the setting to the auto voltage, then what test set does is that it looks for the optimum voltage that should be applied for a given transformer so that you get the best possible results. So I highly recommend starting the testing in the auto mode, because that would give you the most value out of your testing.
All right, thank you, Dinesh. I'm going to send the next question over to Ken. Ken, the equipment may test in the other transformers with different vectorial forms like zigzag?
Yes, the Ttru3 as well as the Megger winding analyzer will test the zigzag transformers. The Ttru3, being the newer instrument, being a three-phase instrument, does have more capabilities. And so we can test the zigzag transformer in more of the way that it was meant to be tested with a three-phase source. So yes, in addition to the vector, the phase shift capabilities of the device, we would also wrap the zigzag transformer test capabilities into that as well.
All right, good deal. Thank you. Daniel, our next question is for you. Which one should we be doing? A three-phase excitation or excitation per phase?
Okay, well, once again, not in the sense that you should be doing one over the other, but remember, when you can or you do have an instrument capable of doing a three-phase excitation and a three-phase transformer, that will yield more accurate results. So then again, the note is not saying that you should only do this mode, but if possible, if you do have the instrument, it will be a more accurate measurement.
Yeah, and if I could just add on to that, if you're running a three-phase result and it's it's saying that there's a problem with the transformer, then you could go to single-phase testing to try and isolate which phase has the problem. So yes, right out of the gate, I would agree with Daniel. Do your three-phase testing to get your most accurate result. But if you're starting to try and troubleshoot, then you could go to single-phase testing to sort of narrow down where your problem may be.
All right. Ken, while we have you, the next question is for you. Can you please review the TTR error? Specifically, what is the nominal to which the actuals are compared?
So the turns ratio error, and I think we might be referring to this slide here. The percent error that we are comparing against when we look at the plus or minus 0.5% that we're looking at here in this example here, that is the nameplate calculation. So that's going to be the voltage values that are written on the nameplate. So again, when we compare to the ratio to the voltage values on the nameplate, it is not the same as comparing the actual physical number of turns that exist inside the transformer. That is why they are given such a wide percent error range from plus or minus 0.5%. So all of the testing that you're going to be doing in the field, all of the testing that is described in the standards are to that plus or minus 0.5%. To allow for that discrepancy again, where the voltage values that are on the nameplate do not correspond one-to-one to the number of actual turn steps within the transformer. I hope that answered that person's question.
All right. Dinesh, is there any relation between rated voltage and excitation voltage for testing?
Before I answer that, I'm really glad to see these questions coming up, because these are the questions coming from people who have experienced these things in the field. So just think about what is happening when you're doing the excitation test. You are basically doing an open circuit test, and you're applying a voltage to the primary side or the high voltage winding, and you're recording the excitation current. And the excitation test is a voltage dependent test. If I try to run the test at 500 volt, 1000 volt, and 5000 volt, I will get different excitation current measurement. Now the question is asking about the relation between rated voltage and excitation voltage. You don't want to exceed the rated voltage when you're performing the excitation test, and you want to apply as high voltage as possible, not to exceed the rated line to neutral voltage. So that's the only criteria I would be mindful of. But as I said, like excitation test is a voltage dependent test. So if you did the test at 10 kV today, make sure that your subsequent tests are also performed at the same voltage level for trending and analysis purposes. Do not use different voltages, as that would impact your trending capability.
All right. Daniel, in the tap changer example of ratio errors, were you compensating for the different tap voltages as compared to the nominal tap voltage?
Okay, well, this is obviously referring to a slide in the presentation. I don't know if you can go to that one. But in the meantime, I can tell you. So remember, when any type of tap changer, being de-energized or on-load tap changer, is involved in our testing, right? Especially, for example, for a commissioning where we want to make sure the tap changer that was wired correctly and is working as expected. You have to run the test through all the positions of the tap changer, right? Again, when possible. There are certain scenarios, for example, a DTC being a long period in service. Sometimes we just don't change the position. We leave it at whatever it is, the service position. But again, when you do have to run the whole run of positions in the tap changer, you do as many tests as positions you have in the tap changer. So you have the voltage ratings for those positions in the nameplate of the transformer. So the software, neither the software or the instrument itself is doing any compensation. You're actually measuring the ratio for all the different positions. And then with each result, you compare to the corresponding ratio that you calculate from the nameplate. So no compensation, is just a measurement of all the different positions, and then you compare to the respective, the corresponding position from the voltage table or from the nameplate, and then obviously you can calculate your errors for each of the positions of the tap changer.
All right, thank you, Daniel. I think we have time for one more question before we need to move on. And as a reminder, if we don't get to your question today, we will be following up with you offline in the coming weeks via email. Ken, our last question for this session is going to be, does the Ttru3 and older tests show the 30-degree phase shift of the delta Y transformer?
So I believe you're referring to the results that you would get from the testing that you perform. And in the version of the software that we're preparing to release, we have added a setting into the software that would allow you to view phase deviation from a relative phase position. So we're talking about phase deviation relative to DYN1. DYN1 is a 30-degree phase shift. So if there was a phase deviation on phase A of 0.5 degrees, we would say the phase deviation is 0.5 degrees. If you wanted an absolute phase deviation, then we would display that as 30.5 degrees. So yes, the Ttru3 is capable of showing phase deviation in terms of relative to the vector configuration or absolute from 0 degrees.
Okay, if I may add one point to this one, because it's important to mention that that the 30-degree phase shift that you're talking about, DYN1 represent the 30-degree phase shift. That is a phase shift between a line-to-line voltage on the primary side to the line-to-line voltage on the secondary side. Okay, and that 30-degree phase shift comes from one side being delta, other being Y. And if you talk about YN0, there's a 0-degree phase shift. But the phase shift that we are calculating during a turns ratio test is between an A phase winding of primary side to the A phase winding of the secondary side. And in theory, the phase angle between phase winding of the corresponding high and low side should be 0 degrees. And if you get a 0.5 degrees or something like that, then that's your phase deviation error. But I just want to make sure that we understand that the 30-degree phase shift that question is asking is for line-to-line value phase difference, And what TTR is calculating is from phase, A phase of primary side to the A phase of the secondary side. So these are slightly different things.
All right, thank you for that addition, Dinesh, and thank you, Ken, for presenting today. With that, we're going to wrap up the Q&A session for our first presentation and jump into our second one, which will be presented by Samir Karkani. Are you ready for this, Samir?
Yes, of course.
All right, presenter mode coming your way. Beautiful.
All right. Good afternoon and welcome all of you. Thanks for joining us today. I would like to thank Ken to present the TTR-U3 part. It was really insightful. So my name is Samir Kulkarni. I am going to be presenting today the second part of winding condition assessment that discusses excitation current and winding resistance. So let's go over the agenda real quick. So we are going to look at what is the purpose of these results, and Ken already alluded to the reasons and the fundamentals of why we want to do that. Then we'll look at some internal specifics of the transformer that affect both these tests, namely excitation and winding resistance. And after that, we look at what are the measurement principles that are involved in doing these tests. Of course, considering we are testing with equipment out in the field, we want to make sure that we are understanding the safety implications and safety considerations. Then we look over some of the results and the analysis tools that we use to understand and interpret our testing. Next, we will look at industry standards, and we will look also at products and applications, and then we will end with summary. So as was discussed in the beginning of our seminar today, that there are two different types of tests. And for today's Substation best practice seminar, we will be looking at the mechanical side of tests and concentrating on winding resistance and core excitation current. So we'd had this discussion before that we are going to concentrate on the windings and looking at maybe turn-to-turn shorts or loose connections. And if we have tap changers, we want to look at and understand if there are any high resistance connections in the mechanism or if the continuity of tap changers is affected. And then finally, with the excitation current, we are going to understand the workings of the core to see if there are any flaws such as shorted laminations, ground faults, or any structural defects. So to get an understanding of when these tests are performed, we can look at different types of factory tests during manufacture. And when that transformer is manufactured, it's tested and then it's sent to the location where it has to be put in service. So during installation and commissioning, these tests are performed. In addition, once you have initiated the service life of this transformer, you would want to perform routine maintenance. So winding resistance and excitation are performed on a routine basis for transformer maintenance. And then if you have internal inspections or any kind of troubleshooting because of a transformer fault, or if a transformer was involved in clearing a fault, you would want to perform these tests to determine the status of your transformer. So let's go over the fundamentals. So you should be able to see now the equivalent circuit of a transformer. So today we are going to discuss magnetizing current, so excitation current, which is the current required to magnetize the transformer core. And then we will be looking at the DC resistance of transformer windings. And you can see here, there are a few more components involved in the transformer equivalent circuit that could affect the measurement of these values. So now I'm going to start discussing the excitation current testing section of this seminar. So let's go ahead and understand what are the measurement principles involved in the excitation current test. So the idea of a transformer is that you energize a primary winding of the transformer and you get a voltage at the secondary side. Now, there is one common link between these two windings, that is the core and the flux that's generated in the core. So once you excite the primary winding, you establish what you call a working flux in the transformer core that links with the secondary winding, and that's how your transformer action takes place, and you get a secondary voltage induced on the secondary side. So To establish this magnetic flux, you need energy. So energy is required to set up this flux in the core, and this flux can be measured in terms of excitation current. Now understand that this is a diagnostic test. This is not a destructive test. So we are trying to diagnose the condition of our transformer system, especially windings and the core, and we are also studying the open circuit characteristics of the transformer windings. So we are looking at two parts of this puzzle here. The first is we are understanding how much energy it takes to establish that working flux within the transformer so that it links to the secondary side. And we are also understanding how the primary winding is going to behave in an open circuit condition. So let's look at some more details on the test. So what kind of signals are applied? So we apply an AC signal, and we apply that signal such that maximum stress is induced on a turn-to-turn basis. However, this stress should not exceed the stress when the turns would face during the rated conditions. So this stress should not exceed the rated voltage. Transformer action works in a way that every turn of the primary and the secondary winding generates a voltage. So you have volts per turn. And once you have that volts per turn, that's multiplied by the number of turns. And then that's how you make up the voltage of across the entire winding. That's why it's so important to go to that building block of that transformer winding to induce stress on that to make sure that this stress is not breaking down the insulation. And however, again, I would like to reiterate this, that the stress that you have to induce in the excitation current test should not exceed the rated voltage. Now, once we understand that we have to use AC voltage to apply, this voltage is applied at rated frequency. And as far as the test mode, the test instrument should be in the ungrounded specimen mode because you're looking at the winding and the core. Now, we saw in the previous slide that this is an open circuit test, and testing for excitation current is conducted on a per phase basis. So you energize each phase, and that is pertaining to the high voltage winding. So you energize each phase of the high voltage winding and determine as an output, you get watts loss and the winding current. So it tells you the amount of current that was absorbed by the high voltage winding and the watts that were consumed in order to perform that. So let's look at now some of the factors that affect this excitation measurement. We discussed in the previous part of the seminar that the excitation current test is a voltage dependent test. So of course we have our voltage that will affect how my excitation current is going to respond. Next, we have core design. So you could have different inductive and capacitive components in the core that could affect how your excitation current trace looks like. Then if you have tap changers in the transformer, that is going to affect, and that is the test setup for your excitation current. For example, if you have preventative auto transformers as part of the load on-load tap changer, the test requirements are different than not having a tap changer, and that's why your excitation current response will be affected. And lastly, you have winding configuration. So depending on whether it's a Y winding or a delta winding, you will see different patterns of excitation current. And we will discuss these factors in more detail as we go forward. So first, let's look at the voltage dependency section. So excitation current magnitude can change with the applied voltage. And because of this nature of the test, industry standards have agreed upon one value at which excitation current has to be reported, and that value is 10 kV. So the way it works is excitation current, a voltage of 10 kV is applied to the high voltage winding. As long as this 10 kV does not exceed the rated voltage, a value of 10 kV is applied, and the current that's consumed by the primary or the high voltage winding is measured. Now, there could be situations where the 10 kV voltage is not achievable, or the transformer might have rating that's not as high as 10 kV. In those cases, a linear approximation is used to determine a 10 kV equivalent value. So you might have a test performed at 5 kV, but then an equivalency using linear approximation is made, and you get an equivalent value for 10 kV. So you can see here, the table to your right hand side, you have a single phase transformer that's been excited at different voltages starting from 1 up to 10 kV, and you can see the excitation current having a different value for each voltage. So that's what I mean by having the voltage dependency. And if you look at the first row, you have a voltage used of 1 kV with the excitation current of 1.22 milliamps. Now that current was linearly approximated to be about 12.2 milliamps at the 10 kV value. Now, it's very important to understand here that a linear approximation is used. It may not be possible to always test at 10 kV. So when comparisons are made, it needs to be understood that actual values are at 10 kV might be different than the values that are equivalent generated at 10 kV. And this is because of the non-linear nature of the transformer core response. And as far as best practices, it is important that we use the same voltage magnitude so that we can compare our historic data at the same level. So let's look at safety considerations. We understand the measurement principles. Now let's look at what kind of safety considerations we have to follow when we are performing excitation current testing. So it's important to understand here that on the outside, all phases are isolated. As you can see here, you have bushings that are separate from each other. However, internally in the transformer, you have all of those linked together with several components, including the core. And that is why it is important to understand that although we have a phase-to-phase, or excuse me, a per phase testing methodology, all the other associated windings will be energized and they will be at floating potential. So it's very important to have to be cognizant of that fact. However, there are exceptions. If you have a Y winding that has a grounded neutral, that connection is maintained even during excitation tests. So you don't have to lift leads, for example, for that situation. You would maintain that grounded connection. And of course, you could have some transformer configurations where some of the terminals are normally grounded. So that will not change. Now, we saw in the beginning of our seminar that we did get excitation current values from a turns ratio test. However, that voltage level was on the lower spectrum of magnitude. With the excitation current that we are discussing now, that is a high voltage value. So it is very important to follow the right safety protocols while performing this testing. Now, let's discuss briefly about residual magnetism. And you could have situations where the transformer core will have residual magnetism. One of the prime examples is after performing a DC winding resistance test, and we'll discuss that further in our presentation today. Or there could be another situation where the time at which the transformer is disconnected from the grid, that might leave some kind of remnant magnetism in the transformer core. Now, how that affects your excitation current readings is that you could see a higher than normal magnitude of excitation current. And that, of course, is not representative of the condition of your core. And the best way to combat that residual magnetism is to demagnetize the core. And we will discuss demagnetization in more detail in the winding resistance section. But in short, what you would do is you would change the polarity and the magnitude of the test current to demagnetize the core, and we'll discuss that further. Now we have understood what are the basics or the building blocks of excitation current. So let's look at the types of results that you would get and what kind of analysis we could perform by using those results. So in excitation current results, we have 3 typical excitation patterns, and these patterns are unique to every transformer. So namely, if you see on the right hand side of your screen, you have 3 patterns. The first one is the high-low-high pattern. The second one is the low-high-low pattern. And the third one is an all-similar pattern. And we'll go into details of these types further in the presentation. Now, note here that the current patterns can be affected by different aspects winding configuration, and core design. We saw that we introduced those terms in the beginning of the presentation as something that would affect excitation current. So we'll look at that in detail. So let's look at the high-low-high pattern to begin with. So in this pattern, as the name suggests, you have two phases that have a higher excitation value. Generally, that is with the outer phases. So the A phase and the C phase will have a higher excitation value, whereas the inner phase will have a lower excitation value. And this depends because the path that the magnetic flux has to take is different for the inner phases versus the outer phases. And this path can also change how your excitation current results come out. This is again a very common pattern that's seen across transformers, and this pattern is also seen across different transformer core designs. So if you see on your screen, you have a core type design to the center, and to the right hand side you have a shelf type design. In the core type design, you have the windings that are engulfing the core and the windings are on the outside, whereas on the shell type, the core is engulfing the windings such that the core is on the outside. So I would like to bring back the point of magnetic flux. So for example, in the core type design, you have the middle phase that has to travel smaller distances in order to establish that mutual flux. And that's why the excitation current required for the middle phase is lower. And that's how you get that high-low-high pattern. So next, let's look at some results for this pattern. So let's look at this first example. So this is a 13.8 kV transformer, which is delta wound on the high side, and a 2.4 kV transformer that is wounded with a neutral available. And it has a de-energized tap changer, but it does not have a on-load tap changer. And you can see here, if you look at the excitation current results, you can see that a test voltage of 5 kilovolts was used, and you get current values for each phase. So you had 119.3 milliamps for the A phase, you have 41.32 milliamps for the B phase, and 119.08 milliamps for the C phase. So you can establish here that the outer phases, the A phase and the C phase, have a higher magnitude of excitation current, whereas the middle phase has a relatively lower magnitude. Now, because this test was not performed at 10 kV, and we discussed in the previous part of our slides that a 10 kV equivalent is used, an equivalent value of milliamps and watts is available. So even with that equivalent, we can see that the high-low-high pattern of 238.54, 82.45 for the B phase, and 238.44 for the C phase has still been maintained. Next, let's look at another example. This one is a 3-winding transformer. So in this one, you have a 132 kV Y-wound primary, a 33 kV Y-wound with neutral available on the secondary, and a 13.8 kV delta wound tertiary winding. So this transformer does have de-energized and on-load tap changers. And this one, you can see, was tested at 10 kV with a value of 10 right here. And you can see the same pattern. You have 16.9 milliamps on the A phase, and you have 12.03 milliamps on the B phase, which is the inner phase, and then you have the C phase that has a value of 17.45. You can see that the outer phases have a higher magnitude, and they're very close in magnitude themselves between the A phase and the C phase. So now let's look at the second type of excitation current pattern. So this pattern is the low-high-low pattern. So in this kind of an excitation current trace is exhibited if you have, for example, a high voltage winding that is Y configured, but its neutral is not accessible. So because the neutral is not accessible, two windings have to be tested at the same time. What I mean by that is when you're performing excitation current testing, you would be testing from H1 through H2. Then you would be switching on from H2 to H3, and then you will be moving on from H3 to H1. Now, how that affects the results is that the results are affected such that measurements that have the B phase or the inner phase would read lower than the measurements that just have the outer phases. What I mean by that is when you're testing from H1 through H2, you're going to have the B phase in this case, So that value is going to be lower. Similarly, when you go from H2 through H3, you're going to still involve the B phase, and because it's the inner phase, you're going to have a slightly lower magnitude of excitation current. Now, if you move on and test from H3 to H1, in that case, you do not have the B phase involved. So that magnitude is going to be higher. So considering you had the B phase involved in two results, you will establish the low, high, low pattern. Now, this kind of pattern is seen in four-legged cores, and we will discuss later in the presentation that sometimes if the correct test protocols are not followed, like for example, not grounding the third terminal on a delta, you would see the low, high, low pattern. And the last one that we will discuss today is the all similar pattern. So in this case, all the excitation current traces for each phase are similar. Now this kind of response is seen for a five-legged core or a shell type transformer, but that transformer generally will not have a delta secondary winding. Now, the other output we discussed at the beginning of the presentation was the Watts loss that's presented. So this Watts loss is the energy used to establish the magnetic flux in the transformer. And that's generally dominated by core loss, which also has eddy currents that are generated in the core. And it is important here to understand that Watt loss patterns are expected to be similar to the excitation current patterns. Of course, these are different quantities. One is current and the other one's watts. However, you can see a same high-low high pattern. You could expect to see the same high-low high pattern even with Watts loss. And in case there are unexpected readings, it's important that if you have an analysis tool when you can compare the Watts loss patterns and the excitation current patterns to determine if it was a questionable reading, whether it was a test setup issue or whether there was an issue with the transformer itself. Now that we've looked at some results, let's look at the analysis section of it. So the industry standards are using pattern recognition to determine and to compare different results. And those pattern recognition that's performed with either historical results. By that I mean, if you have tested a transformer today, and if that transformer was tested at the same voltage level 6 months ago or 2 years ago, you can use those excitation current response curves and compare them to your present day results. Now, you could also have situations where you have comparisons between the phases, which is our next type of comparison. So in between phases, for example, if you have a high-low high pattern, so you would want to compare the two values that are high. So we saw in the previous part of the presentation that the outer phases, namely the A phase and the C phase, have generally higher excitation current values. So comparing those two values will provide some insight on what is the status of your transformer winding and transformer core. The last type of comparison is between similar transformers. Now, this is applicable in situations where you have two sister transformers. If you have two three-phase transformers that are used side by side, you can compare the excitation current values between those two transformers to determine any anomalies or to determine if there's an issue with either the transformer or the test setup. And all these comparisons can be made to get a better understanding. You can also have a situation where you have a bank of 3 single-phase transformers in some of the substations, and then you can compare the excitation current of each phase and determine how each transformer is behaving. And this comparison generally has to be within 10%, or if this comparison exceeds 10%, then you would go into the investigative mode where you would start checking all your connections, you would check your test setup, and one of the most crucial points is to check whether the transformer core was demagnetized or what was the magnetization status of the core before the excitation current testing had begun. With that, we have concluded the excitation current testing section of the seminar. Now we are going to talk about winding resistance measurement. So let's begin. Let's look at what measurement principles are involved in winding resistance. So I would like to bring back the equivalent circuit of the transformer. And now that we've looked at the excitation current that concentrates more on the core of the transformer, we will now look at the DC resistance of transformer windings. You can clearly see here that the resistance of the transformer winding is affected because there is an inductor in series with the resistor. So this is going to affect, and this is going to drive how you perform the test and what results you get. So winding resistance measurement at the building blocks or at the fundamentals is a low resistance measurement. And to make a good low resistance measurement, it's important that a 4-wire method be used. In that 4-wire method, we have two leads that inject current into the test specimen. So in this case, we have two leads that would inject current into the transformer winding, and the other two leads would measure the voltage drop across the winding. Now, we saw in the previous slide that the inductive nature of the transformer winding will not readily allow a change in current. So in order to get a good reading, we need to ensure that the inductive property of the winding is minimized and it does not affect our reading. Now, the way the inductive nature behaves is that it will not allow a change in current. So if the winding is not carrying any current, it won't instantaneously allow a test current of say 10 amps to flow through it instantaneously. So what the winding does is, to counter that change, a voltage is generated across the inductance. So now across the winding, you have a resistive voltage drop as well as an inductive voltage drop. And this inductive voltage drop is represented as L, that is the inductance of the winding, times di over dt. And this di over dt is the rate of change of current. So let's go into more details on that. So this inductive voltage drop that we discussed can be addressed by fulfilling two conditions. One is current stabilization. So we saw that the inductive voltage is generated, or part of it is the rate of change of current. So if the rate of change of current is driven to zero, the inductive nature of the transformer winding will not affect our resistance measurement. And the other important aspect of that is to ensure that the transformer core is saturated. Now, in order to saturate the transformer core, voltage has to be applied. And the flux that's needed to saturate the transformer core can be defined in the equation you see here. The flux phi is equal to the voltage times the seconds. So it depends on the voltage that's applied to the transformer core and also the time for which that voltage is applied. So we have to make sure that our test setup is such that saturation, the transformer core is driven into saturation. Once these two conditions are met, the final reading is a resistive measurement, and that's how you can determine the resistance of your transformer winding. Now, it's noteworthy here to understand that if you have a large winding, or for example, a generator step up or transformers of that sort that have a larger winding, it could take longer for the reading to stabilize because of the higher inductance of those type of windings. Now let's review the relationships between the voltage that's applied, the resistance that's measured, and core saturation. So if you look on the left side of your screen at say time t is equal to 0, when you are beginning the test, you have the current at 0. That current does not instantaneously change, as you can see from the graph. It takes some finite time to stabilize. At the same time, you're also applying voltage to the transformer core. Now, this voltage initially is higher because you would want to saturate the transformer core. And as time progresses, this voltage now reduces to the voltage drop across the winding. And because of the inductive nature, you will initially have a higher resistance that's measured. The apparent resistance measured by the test instrument is going to be higher, And as the current stabilizes and the transformer core saturates, the resistance value will stabilize and give you a final measurement. Now, on the right side of your screen, we have the hysteresis curve for a transformer core. So you can see that the flux generated in the transformer is dependent on the current that's injected in the transformer. So as best practice, you would want to drive the transformer core to saturation such that the flux that's generated will saturate the core. And you would want to avoid being in any situations where your current value is too low that you have some remnants or you are in the near zero region of the hysteresis curve, because this will give you inaccurate and unstable readings. Now we discussed two aspects. One was current stabilization. So let's look into that for a bit. So the test current magnitude is very important, and because the inductance of a winding is affecting its measurement, a higher current will provide an early current stabilization. That's how it reduces the inductive nature of the winding. However, make note that the test current level should never exceed 15% of the rated winding current. And this is because if you inject more current beyond 15%, that's going to cause heating in your transformer winding. And we know that resistance is affected by temperature. The moment your winding temperature changes, your resistance value is going to change. So by injecting a higher current value, you are pretty much invalidating your testing because it's now affected by heat. So let's quickly take a look at an example. Here we have a transformer that has delta windings on the primary and the secondary side. So it's 13.8 kV on the primary side and 2.4 kV on the secondary side. So this transformer was measured for winding resistance using 3 different values of test current. Initially, a value of 10 amps was used and a resistance of 5.917 milliohms was measured. It took about 101 seconds to stabilize. The same exercise was repeated with a higher test current value of 25 amps and a value of 5.926 milliohms, which is fairly close to the initial value, was obtained. And the big difference in here was the time it took to stabilize was 95 seconds, which was lower than the initial 101 seconds. Now, this exercise was repeated for a third time with a higher magnitude of current at 50 amps. In that case, the almost exact same resistance value of 5.926 milliohms was measured. However, the time taken to stabilize was 80 seconds, which was significantly lower than the 101 seconds that we previously started with. So you can see that with increasing current value for winding resistance, increasing test current will reduce the time it takes to stabilize the reading. However, it is very important for me to reiterate, and as a key takeaway, that the value for test current should not exceed 15%. As you can see in the table here at the percentage rated column, none of the current values have gone beyond 15%. The maximum current we have used is 5.54%. So by using the correct test current magnitude, you are ensuring that you get a good accurate reading and you get that reading quickly. So we understand that a higher test current is better as long as it is within 15%. So typical test current ranges will vary from 0.1 to 15% of the rated winding current. And it's recommended to inject to start your resistance measurement at about 1%. And that's because if the current is too low, the measured resistance may not be consistent, it may not be stable. We saw that in the previous slide where we do not want to be in the near zero region of the transformer hysteresis curve. You want the transformer core to be in the saturated section. So that's why a too low current value is not desirable. Again, I would like to drive this point home that we should never exceed 15% of the rated winding current, because now you are going to start heating the winding, which will change the resistance and give you an inaccurate reading. The second factor that we discussed was the open circuit voltage. So we defined that the flux that's needed to be established in the transformer core is a function of the voltage applied and the time for which the voltage is applied. So you can see here, phi is defined as the product of voltage times the time for which the voltage has applied. So if you use a higher voltage that's applied to the core, for the same value of saturation flux, the time it'll take is going to be lesser. So the higher voltage you apply, the lesser time it'll take the core to saturate. So that's how we will look at example 2 here. So this is a DYN1 transformer. So it's delta wound on the primary side and a star wound on the low side with a neutral. So for this transformer, a winding resistance measurement was made with a 10 amp test current with an open circuit voltage of 40 volts. So all three measurements on the low side were made where we got a 13.86 milliohm value for A phase in a minute 7 seconds. Similarly, for the B phase, you had 13.88 milliohms in 35 seconds, and then you had 13.95 milliohms in a minute and about 2 seconds. This exercise was repeated at a higher voltage. Remember that a higher voltage would require lesser time, and that's exactly what we see. So with the same test current at 10 amps and a higher open circuit voltage, the almost exact same readings of across all three phases was obtained. But in this case, the A phase took just 38 seconds, the B phase took 21 seconds, and the C phase took about 33 seconds. So you can see the significant change in the time it takes for your readings to stabilize. And this does not affect the accuracy of the reading. So by ensuring that you use the proper test current range and the proper open circuit voltage, you can make sure that you get a fast and an accurate reading. This becomes really important when you are testing several transformers at the same time, or you have a commissioning test where you have to cycle through all associated tap positions. So selecting the right voltage and test current magnitudes will ensure that you get efficient testing with good accuracy. Now, we discussed selecting the right magnitude of test current. And again, this was because of the temperature dependence of resistance measurements. We know that resistance is a function of temperature, and that's why all the readings have to be converted to a reference temperature in order to perform sound comparisons. So for transformers that have a rating of 55 degrees C rise above ambient, all the readings are converted to 75 degrees C. Similarly, if a transformer has a 65 degrees C rise above ambient, those readings are corrected to 85 degrees C. And you can see here that the resistance that's desired at a particular temperature is affected by temperature values of the reference temperature and the temperature at which the original measurement was made, and of course by the type of your winding material. So looking at a couple of an example real quick for this condition, the low voltage winding was tested. Now it is very crucial that the transformer test conditions be used when you are testing for winding resistance. So you have to document the ambient temperature, the humidity, the weather, including oil temperature, and most importantly, the winding temperature you can see here. And that's typically done by looking at the transformer winding temperature gauge locally at the transformer, because this will set up what we see in the bottom part of the screen, that when you correct those readings to a reference temperature, in this case 85 degrees Celsius, you get a good comparison to previous data that might be done a few years ago, or even factory acceptance data. Now we understand what are the measurement principles for winding resistance. So let's look at an important aspect, which is safety considerations. And the safety discussion for winding resistance is probably one of the most crucial in understanding the whole test. So at the beginning of our winding resistance discussion, we stated that the inductive nature of the winding will not allow a change in current. And the same concept has now to be applied after the test is complete. So you have selected the correct test parameters, you have completed the test, and you have a good measurement. Now, this because this operation involved injecting energy into the transformer winding, it is important that the stored energy should be discharged. So we know that inductor an inductor will not allow that change as easily. So if the transformer winding is not correctly discharged, and if there's some energy left in the transformer, when you disconnect your DC source through the leads, a large voltage will be induced across the winding, which is also called as inductive kickback. And this large voltage can cause arcing to occur at the point where the connection is broken. And the voltage that's involved in this can be high enough that it could be lethal and injure the personnel, and also it could injure the transformer under test and the test instrument. So one of the key aspects of a test instrument that it should be able to dissipate that stored energy in the winding. So you should have ground circuits that are in place to absorb that stored energy using limiting resistors. Generally, a two-step process can be followed to avoid any accidents. So once the test is completed, the test current should be brought down slowly to 0. And once that is complete, the test object, in this case a transformer, should be discharged by dissipating that energy through the ground circuit using limiting resistors. Once those two steps are complete, a visual indication should be available on the test set so that the operator is now aware that the stored energy in the transformer is discharged and that the leads can now be disconnected safely. Remember that the inductive voltage kickback can be high enough that it could be lethal. And considering you could be in situations where you're on top of the transformer, that inductive kickback can be severe enough that you could even be knocked out of the transformer, and that could prove lethal. Now, we touched on demagnetization or residual magnetism in the beginning of our section here. So let's talk about that in detail. So the IEEE guide C57.152, which is the diagnostic field testing guide, mentions that the effect of residual magnetism can be present based on either the time at which the transformer was disconnected from the power line or because of DC winding resistance measurements. Now, this residual magnetism will affect the excitation current measurement, as we saw, and those values can be higher than normal. Again, this would not be representative of the transformer core. So in order to demagnetize correctly, what are the steps to be done? So we use a particular test current magnitude to perform a winding resistance measurement. Let's take 10 amps in this case. If 10 amps were used to make the winding resistance measurement, that same magnitude should be used, and the magnitude of that test current is varied in polarity. As you can see at the center of your graph here, the polarity of that test current is varied, and the magnitude as well. It goes from 100% further down. So what this does is this ensures that the transformer is effectively demagnetized. Now, one of the best practices for demagnetizing the transformer is to ensure that the demagnetization process is initiated on the primary or the high voltage side at the center phase. So you can see that a test current of 10 amp has been used to demagnetize the transformer in this case. And you can see that the transformer test instrument will go through several cycles. You can see it started with cycle 20 at about 10 amps, and it moved on to cycle 16, so on and so forth. So it is going to change the polarity and the magnitude of test current, as you can see here, and that's how effective demagnetization can occur. Now, let's move on to the results and the analysis section of winding resistance measurements. So let's look at de-energized tap changer resistance measurements. You can see that this de-energized tap changer has 5 taps, with the third tap being nominal, and resistance values have been reported. You can see that a graphical representation is available because this will help in more effective trending. You can see the reading stability indicators at 99.9 and a winding difference which is 0.2% on an average, which is within the acceptance criteria. And we'll look at what the acceptance criteria are further in the presentation. The next slide discusses on-load tap changer results. So in that, the top one is representative of an on-load tap changer which has an auxiliary transformer known as the preventative auto transformer, which has a smoother transition between taps and through the nominal. the trace you see at the bottom is a resistive type tap changer with a reversing switch, which will have a more steep and a V-style curve in resistance measurements. Now, an important aspect is to have a graphical representation so that you can pick up any issues that might be occurring. Now, this becomes especially important when you have an OLTC measurement. So at the top right of the screen, you can see that an OLTC has been used to make winding resistance measurements across 33 taps. So you can have a very stable and a measurement that's within acceptance criteria, whereas on the bottom center of your screen, you can see a couple of taps that have a slightly higher value of winding resistance. Now, these situations could be representative of a potential issue with the tap changer, and issues like coking, which will result in a higher winding resistance. So that's why it's so important to have a graphical interface or a graphical representation of the results, so that if there is any issue with test setup, that can be isolated, or if there is any equipment problems, those can be picked up and you can determine the options going forward. Now, we will discuss the analysis part of the results. So generally, results are compared to between 2% and 5%. And this agreement is done across phases or factory results or manufactured data. What I mean by that is if you have winding resistance measurements for each phase, those values should be within a neighborhood of 2 to 5% among each other. So that's how you would compare between phases. You could also have situations where the transformer had been tested for winding resistance at the factory per standards, and you can compare those factory results to your present day results. There's an important caveat there, though, that it's crucial to have the resistance values at the same temperature. So they need to be corrected to the same temperature to make a sound comparison. Now, in cases where there's factory data that's not available, you can go back to the manufacturer and discuss with them what could be typical values that you could see for winding resistance for a particular type of transformer design. Now, these comparisons are also made per phase, as we discussed. For Y windings, that comparison is made for each phase, and if you have a delta windings, that comparison is made between a pair of terminals. Now, it is very natural that depending on field testing, depending on the type of transformers, you could have situations where the results are not within the acceptance criteria. So if that is the case, there are other complementary tests that should be performed to get a better understanding on your winding condition. So as we discussed in the beginning of the seminar, you have the turns ratio test that will give you an idea of the winding health. In addition, we have the excitation current test that we discussed just here before a while ago. And then you have other tests such as leakage reactance and sweep frequency response analysis, or also known as SFRA. So it is a combination of all these tests that should be utilized when questionable results are obtained. So it should not be a unilateral decision. So you should rely on data that is consistent across all such tests to make sure that your winding condition is acceptable or maintenance is required. Now let's look at the industry standards that govern both of these tests that we looked at today, winding resistance and excitation current. So both these tests are mentioned and covered in international standards such as the IEEE standard C57.12.90, which is the test code, and IEEE standard C57.152, which is the diagnostic field testing guide. NETA also has specifications through its acceptance testing specifications and maintenance testing specifications that deal with excitation current and winding resistance. So IEEE, as we saw before, it will have a comparison between phases or between factory results at the same temperature, or it recommends referring to the manufacturer for representative values of both quantities. Next, NETA talks about excitation current consistent such that two phases will have a similar higher magnitude and a lower magnitude is encountered on the third phase. Generally, this third phase will be the center phase. As far as winding resistance, NITA has recommended winding resistance to be performed on dry type as well as liquid filled transformers. Now, these comparisons have to be temperature corrected, and as long as these comparisons are within 1% for dry type transformers and 2% for liquid immersed transformers, those results are deemed acceptable. Again, if you find yourself in situations where these acceptance criteria are not met, it's important to also perform complementary testing such as turns ratio and excitation to get a holistic view and to confirm whether there's an issue with the transformer winding. Now, as far as tap changers, it is recommended that by NITA that the winding resistance be performed on each OLTC tap position. That's the best practice, but there can be situations where that testing is optional because the in-service tap position should not be changed. If that's the case, you can perform that at the in-service taps. Now let's look at some products that Megger has to offer that perform these tests. So for winding resistance, we have our MTO series that has the MTO 210, the 250, and the MTO 300 series models. Next, we have the MWA series, namely the MWA 300 and the MWA 330A. And then for excitation current and power factor testing, we have the Delta 4000 series. So let's look at the Delta 4000 series. It has an output voltage of 12 kV that's continuously adjustable. It has several output current ranges with a continuous current range of 100 milliamps. It can measure a watt loss of up to 2 kilowatts, and it can provide a 10 kV equivalent watt loss. Now, at the beginning, in the excitation current section of our presentation, we saw different patterns of excitation current. And one of the patterns was the low-high-low pattern. Now, this pattern can be obtained because of specific core designs or specific windings. But there was one situation where if the proper testing protocol was not followed, you could get this result. So right here, you can see that we are using a delta Y transformer, and the delta side, which is the primary side, is being tested for excitation current using the delta. So in this case, the H1 and H2 windings are being tested. The H3 winding has to be grounded. So that practice has to be followed in addition to being in the UST mode to ensure that accurate and reliable test results are obtained. The Delta 4000 series has different modes. As you can see, it has modes for power factor testing, excitation current specifically, and it also has a manual test. And the Delta control software can be used to choose the test mode that's most suitable. For power factor, you would want to choose specific test modes, and for excitation current, as you see here, the UST-R mode is used. Ungrounded specimen test mode is used. It can also be used with remotely to control using PowerDB. And one of the important aspects of the Delta is that it will provide a connection diagram after you've entered the correct nameplate data. So this will preclude any errors because of hooking up the wrong leads to the wrong terminals, and that's an error preventing tool. Next, we look at the MTO series. We discussed the importance of the test current magnitude and the open circuit voltage that the importance it carries in winding resistance measurement. So we have a 10 amps current value that's supported by the MTO 210 and the MTO 300 series, whereas a 50 amp value for the MTO 250 model, which goes into a higher current. So if you are in a situation where you have a winding that has a very high rated current, a 50 amp value might be more suitable. Now, the next aspect was the open circuit voltage. This is very important to ensure that the transformer core is driven into saturation to get a stable resistance measurement. So for the MTO 210 and 300 series, you have an open circuit voltage of 40 volts, whereas for the MTO 250, that open circuit voltage is the 50 volts DC. Of course, to address the safety concerns pertaining to winding resistance measurement, the MTO series has built-in discharge circuitry as well as auto demagnetization features. And if you have our similar equipment such as the Ttru3, that lead set can be used with the MTO to perform testing. Now, the next series of our products is the MWA series. The MWA series can output a current of up to 10 amps and has an open circuit voltage of 40 volts DC. It of course has a built-in discharge capability and auto demagnetization. So you don't physically have to change the magnitude or polarity as was done many years ago, which was at that time that might have been the available practice. But with newer technology, auto demagnetization has become completely within the test instrument. Of course, the leads for the MWA are compatible with the TTRU3 leads, so you can have the TTRU3 and the lead set for the TTRU3, and you can also use those same lead sets with the MWA. Of course, it has PowerDB to document your test results and can be used from PowerDB to be remote controlled. Now let's summarize. So as far as excitation current, we know that this is an AC test which will diagnose the open circuit characteristics of the winding and give us feedback on the state of our transformer core. Because of the voltage dependency of this test, industry standards have accepted a value of 10 kV that has to be used, at which excitation current has to be reported. So you energize windings at 10 kV and you report the excitation current. Now, if you do not have the 10 kV value because the transformer is not rated or the 10 kV is not achievable, an equivalent value is available. However, it needs to be noted that linear approximation is used. So when you're comparing test results, you need to be cognizant of that fact. Now, because magnetization is going to affect your excitation current readings, it's very important to have the prior knowledge of the magnetization status of the transformer core. To analyze results of excitation current, pattern recognition is used to interpret and detect any issues. And there could be situations where transformer design could affect the excitation current pattern. We saw that for a core type or a 4-leg transformer, the excitation current pattern can be different. And because of this nature of the excitation current, comparison of results with historical data or with similar data for other transformers will prove beneficial to get an accurate assessment of your transformer and your winding. As far as winding resistance is concerned, we saw that core saturation and current stabilization are key to have an accurate and stable resistance measurement. You could have situations that the winding inductance will drive the amount of time that it'll take for the resistance measurement to stabilize. So by selecting the proper test current and open circuit voltage, you can get an improved stability and core saturation, which will give you an accurate and fast winding resistance measurement. Of course, that considering the fact that temperature is a key factor in resistance measurement, temperature correction should be made when we are comparing, especially with factory results. And comparing with other industry standards and with other complementary tests becomes very important when questionable results occur. With that, I have concluded the winding resistance portion of our presentation, and I think Mike will take over now. Thank you.
Yep. All right. Thanks a lot, Samir. So at this time, obviously, the presentation portion of the second segment has concluded. We'll take a few minutes to answer as many of your questions as we can. If you do have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a brief survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future seminars. On the survey, there's also a field where you can request a demo or a quote on any Megger products. A copy of these presentations, a certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars. All right, let's jump into your questions. The first one I have is for Dinesh. What other tests on transformers do residual magnetisms affect?
Again, good afternoon, everyone. So when we talk about residual flux or residual magnetism, any test that has to do with the core of the transformer would get affected by that. Some of the tests that would get affected by are the tests like excitation current. That is one of the tests that can get affected by this thing, because you are trying to measure the core excitation. SFRA, sweep frequency response analysis, is one other test that can show the effect of this one. When you are trying to do the SFRA test in the lower frequencies, if your core is magnetized, it may not match with the previous baseline measurement. It is always a good practice to perform a demagnetization anytime you think either if the core has residual flux, or if you are performing a DC winding resistance test, you should demagnetize at the end of the test. And IEEE 57.152 standard does mention this thing, that you should perform demagnetization at the end of the winding resistance test, or perform the test that can get affected by residual flux. You should perform those tests before the winding resistance test. So one way or the other, you need to take into account the effect of residual flux.
All right, thank you. Daniel, next question is for you. Which high voltage LTC and DETC taps would you recommend for excitation tests during factory acceptance testing? Daniel, we've lost your audio. You might want to check your mute status. All right, well, while Daniel sorts out his audio issue, we're going to jump up. Yes, there we go.
Apologize. Yes, I was muted and didn't notice. So yeah, the person asking the question specifically is referring to acceptance testing, right? If we look at the standard C57.93, which is the guide for installation and maintenance of liquid immersed transformers, they only mention low tap changer, and they say if the low tap changer is present, again, this is for acceptance, they recommend to run the test in all taps, right? If we look at the field guide for transformer testing, the recommendation is a little different. And again, just taking into account that the question was saying just acceptance, but in the field, if a low tap changer is present, the recommendation is to test in half of the total of low tap changer position, the neutral in case that the neutral is not right at the middle, and one position above and one position below the neutral, right? If the DETC is present, again, for field measurements, this is typically dictated by the in-service position, right? But then again, for acceptance, the official recommendation from IEEE is calling for a test on all taps.
All right, then. Dinesh, the next question is for you. Speaking of not exceeding 15% of rated current, does that mean that winding resistance testing should not be performed on a transformer until it is physically cooled down during a shutdown?
Okay, so that question is kind of interesting. It has two parts to it. As Samir mentioned in his presentation, that winding resistance test does get affected by the temperature. And let's take the first case scenario when the transformer was just taken out of service and the winding temperature might still be in like 50 degrees C or something. As long as you record the temperature and correct your readings to 50 degrees C, then you should be fine, because you have taken into account the temperature. Now, what the other thing that you need to keep in mind is that, let's say you recorded the temperature, and you are using, let's say, 20% or 25% current for your testing. Now, what that would do is that while you're running the test, you may change the temperature of the winding because of the current, and that you have not taken into account because you don't know how much that change is. So that's why the standard says that as long as you stay below 15%, the current would not change the winding temperature. So you don't have to worry about that part. And then let's say if the transformer is hot after it has been taken out of service, just like let's say a few minutes earlier, it is still okay to run the test. Reason being that you're recording the temperature of the winding. Now, keep in mind that you may have to be careful about this thing, because during the time from the moment you took the transformer out of service, the temperature would drop gradually, would drop drastically in the first part, and you don't want to be in the middle of the test. You recorded one temperature and the transformer winding temperature is coming down really fast, then you've not recorded the correct temperature. So the best scenario would be is to wait so the transformer winding temperature is not dropping drastically, and once you know that it is going down at a very gradual pace, that's a good time when you can do the measurement. But again, you want to stick to below 15% of the rated current for your testing.
Thank you, Dinesh. Samir, can we compare the behavior of the excitation current obtained with the TTR test? It should be similar to that obtained in the excitation current test. I would like your opinion if possible.
All right, that's a really good question. So we saw that the excitation current is voltage dependent, and the voltage at which the windings are excited on an excitation current test is in the 10 kV neighborhood, versus for a TTR that we saw was about 250 volts if we did step up, or regardless, it is in the lower spectrum of the voltage. Now, because this test is voltage dependent, the values may not be representative of that relationship when you compare them. It's a voltage dependent test, so making that comparison may not be of a lot of value, and that's because the relationship between the primary winding and the transformer core is not necessarily linear. So the non-linear nature may not provide a lot of value in comparing the excitation current value from a TTR test versus that of a higher voltage excitation, say at 10 kV. So that's why it becomes so important to compare similar data. So it is always recommended, if you have performed a test at 5 kV for excitation, the 5 kV value should be used again to run a test in the future, and those values and those patterns should be compared.
All right, thank you, Samir. Daniel, how can we know that the demagnetization of the transformer was effective?
Well, great question, great question. And as Amir explained, there are a few different methods or algorithms to run demagnetization. So it's a very, very valid concern, right? To check if the demagnetization process was effective. There are some instruments, right, like our tracks, that will actually give you a percentage of remnants before and after the demagnetization procedure. If you don't have an instrument that will tell you that, for example, then a good practice, for example, obviously Samir went over excitation current, right? So if you do have reference values for normal conditions, right, you know what the excitation current at a given voltage is for that particular transformer, you can run again excitation current and compare the results. So that way, again, you know if there is any remnant magnetization in the core.
Thank you, Daniel. Samir, how often should winding resistance and TTR be done on transformers as a part of maintenance?
So great question. So if you look at IEEE standards, if you look at C57.12.00 or 12.90, the winding resistance and TTR tests are routine tests. What that means is that test is applicable to all types of transformers. So even if it's a new design, or even if it's a new transformer, or even if there is field testing. These tests have to be performed or are recommended for all those scenarios. So this test should be part of your normal maintenance routine, and that can be dependent on the type of application that's used. Like some applications might need a more frequent maintenance window. So these will be your basic tests that you would run to assess your winding condition. So whenever you have scheduled a maintenance window for a piece of equipment, performing these tests will give you a great deal of information on the condition of your transformer windings.
Thank you, Samir. Our next question is for Daniel. Daniel, what is the effectiveness of the DETCs and LTCs on winding resistance measurements?
Well, if you have any of or both of the types of tap changers in the transformer, depending on the position you are in for both of them, the path, right? If you're testing, just imagine if you're testing one of the phases, one of the positions, so the path that the current has to go through when you inject it to take the measurement will change if you switch to a different position. So typically, if low tap changers, DETCs are in the picture, if you do have them in your transformer, the recommendation is to test every single position of the tap changer, especially if it's a low tap changer. You want to make sure that that contact system is in good condition, that there is no carbonization or any mechanical issue that is preventing the tap changer to going to a certain position. Another important consideration is to test to make sure, right, the low tap changer by design is built to be able to switch or to go from one position to another without interrupting the current or the flow of current, right, while in service. So that's another measurement, another check you can do, another factor that you have to evaluate when you're doing winding resistance. You can actually, for example, the MTOs, the MWAs, the tracks will have that functionality that will allow you to start a test, let's say at the very top of the tap changer, at the very first position. So you start the test there, take the measurement without interrupting the flow of current. You go to the next position, and the instrument, the software, in conjunction with the software, will tell you if there was an interruption of current, which again, you don't want on a low tap changer. So obviously very important to take into account if you do have those in the transformer under test.
All right, thank you, Daniel. Dinesh, the next question is for you. If we do the excitation test at lower rated voltage, how can we compare to the factory acceptance test data?
Usually when we talk about factory acceptance test data, and I'm talking about power transformers here, usually it's an industry standard to perform the test at 10 kV. Now, there are some factory tests where they might perform the test at rated voltage, but that's not what we are talking about here. We are talking about factory acceptance test data at 10 kV for the transformers that can handle 10 kV. And we should be able to get that kind of information from factory test results. And those are the values that we should be comparing when we perform the test out in the field. Once again, let's say if the factory test data is at a different voltage than the voltage at which you perform the test, I highly recommend not to compare those values, not even the 10 kV equivalent values, because we have I guess a paper or a application note that we published some time back where we clearly showed that if you perform the test at 10 kV and you perform the test at 2 kV and normalize the readings to 10 kV, the 10 kV equivalent readings and the actual 10 kV measurement would not match. So I highly recommend against that to not to use 10 kV equivalent values when you're trying to compare excitation current values. You want to compare values or the test values performed at the same voltages.
All right, thank you. Daniel, the temperature with which we correct the measurement of the winding resistance would be with the oil indicator, or to be more precise, with a measurement off a pyrometer in each bushing. I'd like your opinion on this.
Okay, great question as well. Well, in terms of precision, what you really need, right, is the temperature of the windings, because that's the specimen under test in this case for winding resistance. So in a transformer, you typically have an oil indicator and a winding indicator, right? A hotspot indicator. So that's the one you want to go with, the hotspot. Now, we know that, right, that is not that it doesn't have a probe. It is not reading directly the temperature of the actual conductor, but that is the closest we have in the field. Now, in some power transformers, especially large power transformers, you will actually have an optic fiber probe that will actually give you an accurate reading. If you do have that, um, that's um, that's ideal, again, because that's the temperature you need, the temperature of the windings under test. Now, I'm not familiar with any device that you connect to the bushings for that. I'm myself not aware, but again, just to summarize, go with the winding temperature indicator of the transformer. If you do know the unit has those fiber optics probes that go directly to the windings, that's the best case scenario. Again, that depends on the transformer itself.
All right, thank you very much. I think we have time for one last question, so I'm going to send it over to Dinesh. Dinesh, is there one test set that can perform TTR and winding resistance?
Before I answer that, I would just like to add one comment to the previous question. I forgot the name of the standard. I can find the IEEE standard number, and where they have a formula where if you want to truly and accurately measure the winding temperature, what you can do is that you can take into account a number of things: the top oil temperature, the bottom oil temperature, and then you can have some sensors. As someone is pointing out, you can have those sensors, and in the absence of those sensors, maybe the winding temperature gauge. But there is a formula in one of the IEEE standard that tells you how to kind of more precisely calculate the winding temperature. The gentleman who asked that question, maybe there is a contact information of Samir in one of the slides, and they can reach out to us, and we would be happy to share that IEEE standard number with them. Okay, coming to the last question. So the question is asking if there is one test set that can perform TTR and winding resistance. Before I answer that question, I want to make sure that we understand this thing, that TTR test is a AC voltage test. You apply voltage and measure voltage to get your ratio. And winding resistance is a DC current test, where you apply a DC current and measure the resistance of the winding. So the source requirement for both the instrument is different. One requires AC voltage, other requires DC current. And with the winding resistance, you also need to have a discharge circuitry to dissipate the energy that gets stored in the inductor or the coils. So the requirements are different for the two tests. However, there are instruments available out in the market which can perform both the tests with one instrument. And one of the advantages that for both TTR and winding resistance, you use the same connections. So the lead setup is the same. So if you have one instrument that can perform both the tests, it gives us the added advantage of not having to go up on the transformer and change the lead connection. And whenever you go up on the transformer, it's a safety aspect as well, that getting up and down the ladder can be a safety hazard. So from that perspective, having one instrument that can do both the tests is of great advantage. And Megger has a couple of those instruments like MWA, which is a Megger winding analyzer, and then Megger also has a TRAX unit, which is a multifunctional test set, and both of them are capable of performing winding resistance and TTR from one single test box.
All right, thank you, Dinesh. It looks like that's all the time we have for questions. We apologize if we did not get to yours today, but we will follow up with you all offline in the following weeks. Thank you all for attending. If you could, please remember to answer the survey. The survey at the end of this webinar will include a field for you to request a quote or a demo if you're interested. Once again, a copy of the presentations, certificate of attendance, along with a link to the video recording of the webinar will be emailed to everyone in 2 business days. I'd like to thank you all again for attending and have a great week.